All right, we've made it to our third chapter now. This is our final chapter, our final unit on vectors. And this really was the goal all along. We had to get to this point. This chapter is all about lines and planes in 3 dimensions. And so the problem that we have in 3 dimensions is that we can't use sort of our standard methods for writing equations of things down. The equation of a parabola, for example, works really good in 2 dimensions, but in 3 dimensions it doesn't work so well anymore. So we needed to have an understanding of vectors in order to get to this chapter. And you won't see it, we'll see it a little bit today, but we're mostly just talking about 2 dimensions today, and we're going to build from that. What we're looking at here, I've got a line drawn. This is really, I suppose, a quick little recap of grade 9 math. There's a line. It's in 2 dimensions, okay? Just 2 dimensions here. I'm not tossing in a 3rd dimension at all. And I have 3 equations, and all 3 of those equations represent that line, okay? They're all exactly the same equation, just in rearranged versions. The first one's the one you're probably most familiar with. That's your slope y-intercept form. So your slope is the 3, and the y-intercept is the -5. Right? In grade 9, we're used to that. We plot the y-intercept, use the slope to get the rest of the points. The second equation there is the equation written in standard form. And in standard form, you get everything on one side of the equation equals to 0. You use that a lot more in grade 10 when you're solving using elimination. The third one is really useful, but when you're not as used to seeing, you're probably more used to seeing it if I put a little squared there. Right? If I do that, then it's a parabola, and you can recognize where the vertex is. Well, it turns out with a straight line, it works much the same way. This is called slope point form. And the way it works, similar to the first one, it tells you the slope. Slope's 3. And it gives you a point. And the way you get the point is just like the parabola. You take the -2 and the 1, change the sign of the first and leave the sign of the second. So your point would be at 2, 1. So that gives you a starting point on the line. And then you'd use the slope up 3/1 to get more points, and you go from there. That's actually, I mean, we don't teach it in grade 9. We really don't. I'm sure we didn't show you guys that in grade 9. I've just started showing some of my grade 9 classes in the last year or 2. That form can sometimes be more useful than the first one. Y equals mx plus b is great, but slope point form is often easier to find. And as it turns out, that slope point form is very similar to what we're going to be using with vectors. So that's why I wanted to just show it to you quickly. So here we are, it's chapter 8 in your textbook. We're just looking at 8.1 today, and we're going to do it in 2 steps. So today we're pretty much looking at just 2-dimensional stuff, just to get the ideas across, just to try and figure out how vectors are actually going to apply in these situations. And then tomorrow we're going to skip ahead and look at 3 dimensions. As I say, we're just doing lines right now, but eventually we'll build into equations of planes. So lines using vectors. So first of all, you need to remember, I'm doing everything here in 2 dimensions. We don't need to do it this way in 2 dimensions. Okay, it's not necessary. We can do equations of lines just fine as it is. But our goal isn't 2 dimensions. Our goal is going to be 3 dimensions. So we're going to start with it here because it's easier to picture in 2 dimensions. And then tomorrow we're going to apply all of this idea into a 3rd-dimensional context. So how do we do it? It says we can describe a line in terms of an initial vector and a direction vector that's parallel to the line. And that's what you see in the picture here. We've got that little green vector, which we're calling the initial vector, and the red vector is the direction vector. So the way that this works is we're going to use the green vector, the initial vector, to move onto the line. So you can see it here. We've taken the green vector and we're moving to get to that particular point on the line. Once we get to the line, then our direction vector, since it's parallel to the line, it's going to allow us to move along it. Okay? So in fact, that blue line is the same one I just showed you, right? It's the exact same line. So I'm using the first one, the green vector, to move to the line. And then I'm going to use the direction vector to start moving along it. So what I've got drawn there is one initial vector and then one direction vector. But I've even got them added head to tail, right? The vectors are aligned properly. So if I start with the green vector and add the red vector, I end up at this new point up here, 3, 4, which is actually on the line. But if I didn't want to stop there, I could always use another direction vector, right? I could maybe use the direction vector twice. And if I use the direction vector twice, I still end up at a point on the line. Now notice I've only used the initial vector once. I need to get to the line, and then I'm going to use the direction vector to move along the line. That is just like, forgive me, I'm going to back up for a minute. That's just like what we did here with slope point form. We used a point to start on the line, and then we used our slope to get more points. Same idea now, except with a vector context. This is how we're going to write the line then. Notice I've used square brackets, so we're writing this as a vector equation. It says x comma y, so the vector xy is going to be defined by taking an initial vector, 2, 1, and then adding, it's got a little t there. T is a variable. T times this vector, which we call vector d, and that's called our direction vector. T, as I said, is our variable. It's called a parameter. And t is allowed to represent anything. So any number at all. It doesn't have to be an integer. It could be a decimal. It could be the square root of 53 if you wanted it to be. It can be absolutely anything. But that's allowing for, the initial vector is just 2, 1, right? It's going to move us to the line. But then we're saying go as far as you want in the direction of our direction vector. So the example that I showed there, the first one, I used just one direction vector, and that got me to this point. And then I used 2 direction vectors, and that got me to there. Well, if I wanted, I could use 6 direction vectors or 7 direction vectors and keep moving. If I wanted to, I could make t a negative. And if I made t negative, that would move me this direction on the line. And I have to allow for decimals, because I might not end up at exactly a nice grid point, right? I might end up right there. And so I would need a decimal value for t. So t is called our parameter. It's going to allow us to move along the line as far as we want to go. So can we just become a little bit more familiar with how this is going to work? There's our equation again. Same line. It says determine the point that would be represented when we get these different values of t. So if t is 5, what that's saying is we're using the direction vector 5 times. So I can kind of draw it for you. I can't quite fit it, but that would be the initial vector, right? Get to the line, and then use a whole bunch of those direction vectors. So we need one there, we need another one, and so on. And eventually it's going to move us up to some other point on the line. The way we'll use our equations is we write it this way. We'll say xy is that initial vector, start at 2, 1. Keep in mind, we have to use square brackets because technically this is a vector equation. But at the same time, you can think of it a lot like just points. Okay, it's the point 2, 1, which was a point on the line. Okay, we just need to represent it using vectors. So for this first one, we've got our initial vector 2, 1. Our parameter was 5. Right? We set t to 5. Multiply that by 1, 3. So that's 2, 1 plus 5, 15, which ends up at 7, 16. And again, that's written with square brackets, but it just corresponds to the point 7, 16. So 7, 16 is a point on the line, and we get to that point if we let the parameter be 5. Letting the parameter be 5 is the only way to get to that point, right? If t was a little bit bigger, we'd move past it. If t was a little bit less than 5, we wouldn't have got all the way to 7/16. The next one there, b, if t is negative 2, we'll do this one a little bit quicker. X, y, 2 to 1. Remember, for that initial vector, I can write that as minus 2. That initial vector never has a number in front of it. We can put a number in front of our direction vector because that's telling us how far along we're moving on the line. But that 2, 1, that's just getting us to the line in the first place. What's this one? I'm just going to do it all at once. 0 and minus 5. And that actually corresponds to our y-intercept. That would have been this one we can actually see. We used the direction vector twice in a negative direction, and it takes you right to the y-intercept. Okay? So that's relatively easy to use. Keep in mind one disadvantage. If you think about this equation right here, we're in 2 dimensions, but we have 3 variables. We have x, y, and t. T really is a variable, right? It's our parameter. If we used slope y-intercept form, there was only ever 2 variables, just x and y. So we do have an extra variable in order to handle this type of problem. New line this time. Graph the line 4, negative 1, which is our initial vector, plus t, our parameter, times minus 3, minus 2. So the way you graph these is, well, it's similar to how you would have done in grade 9, right? That 4 minus 1 tells you where to start. So technically it's a vector. I'm going to show it as a vector here. 4 minus 1 takes you right there. That is a point on the line. Right? That's our initial vector. The direction vector is the minus 3, minus 2. And that's telling us how to find more points. So now that we're on the line, right here, we've hit the line somewhere. We just need to find more points on it. So the direction vector is minus 3, minus 2. That looks like this. Okay, that's minus 3, minus 2. But I'm going to use that from the point that we had. So I'm going to go left 3 and down 2 to get another point. And I could do that again, I suppose. Left 3, down 2. It's acting just like the slope, isn't it? Right, there's a direction vector. There's another direction vector. And so overall, if I want to graph the line, now I've got 3 points on the line. We only actually needed 2. There's the line. So we use the initial vector to get a first point on the line, and then use the direction vector to find more points. So is that the only way to do it? Is that the only way to write a vector equation, I guess I should say, for this line? Certainly there's ways to write equations that we've learned in grade 9, but could you write a different vector equation? And the answer is yes, otherwise I wouldn't have asked it, right? What could you change? What are some of the things that we could change so that it actually was the same line, but written in a different way? Well, we could just change the initial vector. Right? I don't have to make it 4, negative 1. I could make it the point 1 minus 3. Still put a t in there for our parameter, minus 3, minus 2. So I've changed this. I've changed that initial vector. It doesn't matter, right? All I needed to do was use that initial vector to get onto the line in the first place. So if I used that, I still end up on the line. I still use my direction vector to find more. I could change that to lots of other things too, right? What's the other one there? Minus 2, minus 5. There's an infinite number of points on the line, so I just need to find one. Other things that we could do, let me change this back, 4 minus 1. Again, that could have been anything, as long as it was on the line. I can change the direction vector a little bit, but I have to be more careful with that. The direction vector still has to move along the line. So I could just use the opposite vector. I could use 3, 2. That would still be the same thing, right? Moving right 3 and up 2 is the same as moving left 3 and down 2. So that still works. The other thing I could do, I'm not really sure why you'd want to do it in this case. but I could scale this up. I could make it 6, 4, right? That's still an equivalent direction vector. It's still moving the same way. So it still represent the line. Generally speaking, we're not going to go in that direction, right? We're not going to change the 3, 2 into a 6, 4. But if you have one that has a 6, 4 as a direction vector, sometimes then it's worthwhile to reduce it and make it a little bit smaller. So that gets us to here. There's lots of different ways that we can write lines now. This is back to that original one, right? So the vector equation's written there. Parametric is new. I haven't told you about that one just yet. I don't know, maybe you can see where parametric's coming from. All that we do to get parametric is we break up the vector equation. So to get this x equation, I take all of the x parts. So x equals 2 plus 1t. And that gets me the x coordinate. And then if I want to get the y is equal to 1 plus 3t. Okay? And there's a reason for that. As it turns out, parametric equations are going to be much easier for us to deal with than vector equations. Vector equations are going to be easier for us to write and maybe easier for us to picture the line a little bit. But in terms of doing calculations and types of questions, the parametric equations are almost always going to be what we want to use. Slope-intercept form we knew about, standard form we knew about. Those are all our old ways. This is just interesting, and it's going to be helpful a little bit later on. So notice, standard form, and that was this guy. Standard form looks like ax plus by plus c equals 0. That's the way it has to look to be called standard form. Well, if I grab these two coefficients, the a and the b, and turn them into a vector, what I'm saying there is that that vector would be perpendicular to the line. Okay, and I can show you that actually. It's pretty easy to show you. From this one, I'm grabbing these two numbers here, the 3 and the -1. So my vector is 3 and -1. Now if I want to show you that it's perpendicular to the blue line up there, I know that the blue line has a direction vector of 1, 3. That's my direction vector. So if this green one, which we call vector n, and the d vector, the direction vector, take a look at those two. There's a 3, -1 and a 1, 3. If we do the dot product of n and d, we get a +3 and then a -3. We get 0, which means that those two are perpendicular. Right, that was one of the good uses of our dot product. So the standard form equation, if we take those coefficients, the vector that we get is always perpendicular to the line. And that particular vector gets called a normal vector. Now I'm introducing this to you now. It's going to become really important in a little while. So it's significant now, really important when we get to planes. Standard form of a line. If we have the standard form, we can grab the coefficients, and those coefficients are going to be perpendicular to the line. Okay? A couple more to go, just a couple examples to try. Here's our line, -2, 3. Got a direction vector. Try a few things. We just want to write the parametric equations first. So to get our parametric equation, it's called that because we're using the parameter. All right, everything's based on the parameter to do this. All we're going to do is break up the components. So the x component was -2. That -2 came from the initial vector. And then the parameter has to get multiplied by the 4 in the direction vector. So x is equal to -2 plus 14. And then the y, that gets the 3, and then -1 times t. And you don't have to put that 1 there, but I got it anyway. That gives us our parametric equations. Now I told you that we wanted to use the parametric equations more often for calculations. And this is a situation here where you'd want to use our parametric equations. Is the point 18 - 3 on the line? Well, that's a really easy question in grade 9, right? In grade 9, you were given equations like that. And if you wanted to know if 18 minus 3 was on the line, you just subbed in those values and you checked to see if it was equal, right? Really simple in grade 9. This is harder now. And the reason it's harder is because we have 3 variables. And we only have 2 numbers to sub in. We have the 18 and the minus 3. So certainly the 18 goes in for the x and the minus 3 goes in for the y. But we have to be a little bit more careful about why we're going to bother to do that. I'll start it. I'm going to sub that in. Put the x in there. Put the y in here. Now, oops. I guess that's okay. That gives us 2 equations. And what we're going to do is we're just going to solve both of them for t. So it'll give us 5 equals t for this one. And if I solve this one, minus 6 equals minus t. So t equals 6. So we got 2 different values for the parameter. What that tells you is that the point isn't on the line. Let's see if you can think of why. Say since the values so in order for it to be on the line, we would have had to get the same value of t both times. So we would have had to get 5 and 5, or 6 and 6, whatever. They had to be the same number. The reason is, if you think about what would happen, if t was 5, then up at the top here, I would sub in a 5 for t, right? Well, that 5 would affect the x component and the y component and give us a couple of numbers. If I sub in 5, notice that for the x component, I would actually get the 18, right? 5 times 4 would be 20, and then take away that 2. I'd get 18 from that. But with the y component, I don't, right? With the y component, if I put the 5 in, 5 times minus 1 is minus 5, plus 3 is minus 2. So I got the right x component, but I got the wrong x component. Or excuse me, I got the right x component and the wrong y component. With the 6 is the number that we would need to get a minus 3 for a y-coordinate. But the 6 isn't going to give you the 18 for the x-coordinate. So we needed both of those to work in order to actually verify that this point's on the line. Okay. I need to move on to C, but we're not going to have quite enough space. Maybe get this out of the way. Here's part C. Determine the y-intercept of the line. Again, this is one of those ones that's really easy from the grade 9 perspective and a little bit harder for what we have to do now. So it's kind of funny, right? Things are actually harder to do with vectors. Determine the y-intercept of the line. Well, we had methods for finding the y-intercept. Anytime you ever want to find a y-intercept, what we did was we just set x to 0. Right? That worked. Well, you did that in the advanced functions course all the time, right? You'd have a crazy function and you just want to know what the y-intercept is, so you sub in x equals 0 and you calculate it really quickly. That's going to work for us here too. From our parametric equations, which as I said is where we do all of our calculations, that's our equation for x. Well, I know that x has to be 0. That's the only way we can get a y-intercept. So if I sub 0 in, I can solve for t. We'd get 0.5. So what that's telling us is that the only way we will get x equals 0 is if t is equal to 0.5. And if t is 0.5, we can sub that into our y equation and then get the y-intercept. So y is equal to 3 minus 0.5. So our y-intercept is just 2.5. But it took those two calculations, right? The first part was figuring out the value of the parameter, and then we figure out the y-coordinate. So, I mean, I do want you to notice that what we're doing right now is more work. Right? It's harder to do these calculations using vectors than it was without the vectors. Of course, keep in mind the reason we're still doing everything in 2 dimensions, and that's not the goal. The goal is to be able to do things in 3 dimensions. Last one for us, determine a possible equation for the line that passes through the points A and B. This is like a really standard grade 9 problem, right? And in grade, I don't know if you remember grade 9 too well. The way we would have done it is, in grade 9 at least, I'll write it down really quickly on the side here, y equals mx plus b. What we do is we'd use those 2 points, and we'd figure out the slope, and we'd put the slope in for the m, and then we'd sub one of the points in and solve for b. And that was our grade 9 method. Worked really good. Always showed up on the test, always showed up on the final exam. Well, now we know vectors, and so we can do things a little bit differently. The way we get our equation of a line now is we do just our normal xy there equals an initial vector plus t times a direction vector. That's what we need, right? So we need to know an initial vector, and we need to know a direction vector. So, well, our initial vector, that's just a point on the line, isn't it? An initial vector is just some way to get to the line. So that could just be minus 5, 9. Pick some point that's on the line. Could have been the other one too, right? Could have been 1 minus 7. That would have worked fine. But we just needed a way to get to the line. Next part that we need is our direction vector. So the direction vector has to move along the line. It's a little bit trickier, but if you think about it, we know 2 points. And so if those 2 points A and B are on the line, then the vector from A to B has to be parallel to the line, right? It's got to be a direction vector. So if I want to get vector AB, what would that be? To go from minus 5 to 1, I added 6. And to go from 9 to I think I subtracted 16 on that one. Yeah, pretty sure that's right. So now I have an initial vector and I have a direction vector. So my equation of the line would be initial vector minus 5, 9 plus t times 6 minus 16. And again, we mentioned before, that's not the only answer, right? I could have switched it. I could have used the second point. I could have used the 1 minus 7. That would have worked fine. And maybe here I actually want to take advantage of the chance to write this a little bit smaller. Maybe I write 3 and minus 8. Right? That's sort of equivalent to reducing the slope in your equation of a line. Both answers totally right. One thing that is going to mean, as you're doing homework questions and comparing answers to each other, there's a very real possibility that you're going to have a different answer than the textbook or a different answer than somebody else, and you can both be completely right. So keep that in mind. That's very possible that something like that could happen. Okay, so there you go. That's the first part of this lesson. All we did today was 2 dimensions, though. So as you're going through the homework, I want you to be thinking about how this will apply to 3 dimensions. I think a lot of it you can see. I mean, even when we just did vectors in the first place, going from 2 dimensions to 3 dimensions, we just added in the third component, right? And that's the same in this case. But think about how that's going to change some of the calculations, right? If we've got a third component in each of those vectors, can we still do these calculations in the same way, or does it mess up some of the calculations?